Namaste and welcome back to yet another lecture on linear algebra through geometry. We have been looking at the idea of linear transformations, mapping one vector to another vector, and we studied some of those linear transformations, which includes rotations, reflection, shear, scaling, projections and so on. We looked at most of those linear transformations. We call them as linear transformations, and then we said that look, most of them are invertible except the projection transformation, which is not invertible. So, towards the end of the last lecture we said okay, let us formally define the linear transformation, and then let us look at what is it that makes I mean at least in the 2 by 2 sense, what is it that makes a linear transformation invertible transformation. That means you go from a vector u to another vector v by a transformation. Can you come back from v to u by the inverse of this transformation that you have used? So, that is a question that we asked, and we also looked at certain interesting examples which we probably would not have made paid much attention to. For example, the shear matrix that we looked at was the one which is used to convert fonts from regular to italics and so on. So, let us look at the idea of in this lecture we will look at the idea of I mean formalizing the linear map or a linear transformation as such, and what we do is we go on to look at what is it in the 2 by 2 sense, what is it that makes a transformation what do you call reversible or an invertible transformation. That is what we are going to look at, right. Okay. So, linear transformation. Okay, we already know that we have, in the previous cases we have seen that transformation is basically changing one vector to another vector, I mean mapping from one vector to the other vector, and we captured that in terms of a matrix. Say suppose, so let us take the suppose A is the matrix representing a linear transformation then the following holds. Then A into alpha u plus beta v is equal to alpha times a u plus beta times a v for some scalars alpha and beta and vectors u and v. Again, have in mind that we are only looking at whatever that is happening in 2 dimension. So, we are just looking at A to be a 2 by 2 matrix, and u and v are 2 component vectors, and then alpha and beta are some real scalars, right. So, this is basically I mean this is actually what you call as your linearity property. That means if you have we know that you have a vector u and you have another vector v, you have a vector u and you have another vector v, then you can write the linear combination of uv, the linear combination of uv as alpha u plus beta v, and that is a vector which is another vector which is let us say w. Now, what we try to say by linear transformation is that the effect of A on the vector w is nothing but the effect of A on the linear combination of these two vectors u and v, which is nothing but the sum of the effects of the I mean the it is basically captured as the the sum of the effects of A on u and that on B, that means beta A v. This is what we call as linearity property, right. And I mean in general, if you see, it also preserves scaling. For example, if I have some scaling factor, I mean everything is captured here. So, for some I will just write it separately. For some scaling factor, let us say factor k, we have A into k u, where u is a vector and k is a scaling factor. We have the effect of scaling the vector and then transforming it is the same as transforming the vector u using A and then scaling it. That is what this means. Okay. So, A into k u is nothing but k into A u. So, we will see that I mean in different terminology, it is also called as the idea of superposition and homogeneity and other things. So, this is exactly what a linear transformation is. And again, let me make the disclaimer that we are just looking at A, which is a 2 by 2 matrix, and therefore, our u v, everything is all these fellows are 2 component vectors. We are just still hovering around 2 dimension space. That is exactly what we are looking at. Later we will get on to third dimension, 3 dimension, and generalize our results to an n dimension and so on. So, having seen the idea of linear transformation, the question that we have in mind is, we have studied a list of transformations like in the previous lectures, where we looked at scaling, reflection, shear, projection, rotation, etc. The question that we had in mind is like, look, we go from one point to another point, we want to come back from that to this again. That means we were looking for some kind of invertibility of your transformation. So, the question is, how do we know that the given transformation that you have, which is captured in terms of a matrix, is an invertible transformation or not? Again, we are going to look at a square matrix, 2 by 2 square matrix. That means we are going to look at only linear transformations which are going to act on 2 dimensional vectors to give you another set of 2D vectors, 2 component vectors to give you another set of 2 component vectors, another 2 component vector. That is exactly what we are going to look at. Okay. So, let us look at something interesting here. So, what do we do now? Consider a transformation which is captured in terms of the matrix A. So, I will just write this as consider a matrix A 2 by 2 as below. So, what are we going to do? I am going to look at A as, let us say, A11, A21, A12, A22. Okay. Now, let us, that means the matrix A itself, you can see that it is composed of 2 column vectors, and these 2 column vectors are themselves 2 component vectors, right. These 2 column vectors are themselves 2 component vectors. So, let us actually plot that and then let us draw that and then see if we are able to make some headway in looking at things. Okay. So, let us look at this. What do I have? I have, let me call this as the A1 vector. This is the A1 vector. Let me call this as my A2 vector. Let me call that as the A2 vector. So, my A1 vector is basically A11, A21. So, let me draw this. Let me complete this geometry there. So, this is basically my A1 1, and the second component that I have is basically my A2 1, which is here. Then this, my second vector has a component which is A2 2, which is the along the y axis or the E2 axis, and this guy is basically my A1 2, right. This is what it is. Now, what I do is, let me just complete this triangle, and I want to find out the area of this triangle. So, I want to find out the area of this triangle, let me call this as T. So, I am going to look at area of triangle T. Area of triangle T. Now, it is easy to say that, see that the area of triangle T, let me capture that as T is given by the, let us take this. So, okay, sorry. The area of triangle T is basically this area that we have here, right, this area, that means the area of that rectangle that I have. So, which is captured by the product of this length and breadth that you have, which is A11 into A22 minus, what else is here, minus, let us call this, let me just draw this. This is basically, okay, let me take another light color. So, this that I have, let me call that as my triangle T1, let me call this guy that I have here as triangle T2, this is T2, and let me call this as triangle T3. So, this triangle I am going to call this as the triangle T3. So, this is basically A11 into A22, that means the area of the entire rectangle that I have, minus I am going to have the area of triangle T1 minus the area of triangle T2 minus the area of triangle T3, right. That is what we are going to have. Now, what is the area of triangle T1? Area of triangle T1 is nothing but, it is half into base into height. What is T1? Half base is into A11 into the height is A21. Similarly, area of triangle T3, area of triangle T3 is nothing but half base into height, again it is half into A12 into A22. Area of triangle T2, area of triangle T2 is nothing but half into T2 is basically A11 minus A12, that is the base that we have, and the height is nothing but A22 minus A21, right. Now, so what we do, we subtract all these things. So, what do we get? We get something interesting out here. So, triangle T, the area of the triangle T is given by A11 A22 minus A11 A21 by 2 minus A12 A22 by 2. If you take the, if you expand this and get the product, so we are going to get minus A11 A22 by 2 minus, that is a minus here, and I am going to multiply this minus A12, that becomes plus A12 A22 by 2. Then I am going to get one more plus, which is basically A21 and A11. I am going to get plus A11 A21 by 2, and I am going to get a negative. This is minus and that is minus, that is plus, and then there is this minus, so which is going to give me minus A12 A21 divided by 2. Now you can see very clearly that you have a lot of terms that get cancelled out. You have A11 minus A11 A21 by 2 getting cancelled with plus A11 A21 by 2. This gets cancelled. Then you have A12 A22 by 2, and that gets cancelled, A12 A22 by 2. So what are we going to have? I am going to have this triangle to be A11 A22 minus A11 A22 by 2 minus A21 A12 by 2, which is essentially A11 A22 by 2 minus A21 A12 by 2. And this is the area of the triangle that we had there. Suppose if I want to extend that, I extend this to a parallelogram. I construct a parallelogram. We already know what it is to do the parallelogram business here. So if I want to convert this to a parallelogram, so I get this, construct a parallelogram. So I get into this. So what is the area of this parallelogram? You will see that this is basically what we were looking at. This triangle's area is what we just found out. So area of the parallelogram, entire parallelogram is 2 times t. So we are going to have area of the parallelogram. So area of the parallelogram is 2 times t, which is nothing but 2 into A11 A22 minus A21 A12 divided by 2, and these two get knocked off. So ultimately what we get, area is equal to, area of parallelogram is equal to A11 A22 minus A21 A12, and that is exactly what we call as the determinant of the matrix, determinant of A, which is typically a scaling factor, determinant of A, where A is the matrix, determinant of A is equal, determinant of A where A is where A is this matrix, A11 A21 A12 A22. Now let us make certain comments about this, and then let us get on to the question that is still remaining to answer, which is basically invertibility case. Let us look at that. Okay, invertibility of the transformation. So what are we going to say? We are going to say that if determinant of A is equal to, let us say 1, then we say that the map, we say that A does not change the, oh my God, A does not change the area. Where did we see this? Let's just quickly recap, revisit our matrix, rotation matrix R theta. R theta was cos theta sin theta minus sin theta cos theta. Now what is the determinant of R theta? We just saw that determinant of A is nothing but product of these diagonal terms minus the product of the off diagonal terms. So we are going to get cos square theta minus of minus sine square theta, which is 1. And remember, we actually made a comment there saying that the rotation matrix does not alter the area, it preserves the area. We also saw that it preserves length. So, we see that rotation matrix R theta, which we defined before in the previous class, is the determinant is 1, right. The determinant of R theta is 1. Does not change the area. Okay. What does not change the area? The linear map A, the linear transformation A does not change the area. Then the second property that we are going to look at is basically this: if 0 less than or equal to determinant of A less than or equal to 1, then the map A, let me put this, the linear transformation A shrinks the area. If determinant of A is 0, we already know what it does. Basically, we will come to this, we will just note down that the matrix is, let us say, rank deficient. We have not defined this rank yet, we will do this when we get to the idea of the subspaces and stuff related to matrix. At a later point, we will get to the idea of rank. Right now, we will just take this as rank deficient. And 4, if determinant of A is greater than 1, then area is expanded, and the most important thing, if determinant of A is less than 0, this is the most important stuff. We are going to say the orientation of objects, the orientation changes. Okay. The orientation of what? The orientation of the object changes. I will say is changed, that is better. Orientation of the object is changed. Okay. Now, how do we even okay. So, what is the role of this determinant, especially for this 2 by 2 matrix? That is something which we are going to see here. We will again do this. Recall Cramer's rule that we studied in module 2. Cramer's rule that we studied in module 2. Suppose I had this A11 x1 plus A12 x2 is equal to B1 and A21 x1 plus A22 x2 is equal to B2. We said that x1 is equal to the determinant of this matrix B1 B2 A12 A22 divided by determinant of A11 A12 A21 A22, and similarly x2, we told that x2 was this determinant of this matrix A11 A21 B1 B2 divided by determinant of A11 A21 A12 A22, and we said that if determinant of A is not equal to 0, then A is invertible. That is precisely what we have here. If you want a linear map to be invertible, the determinant of the linear map must be not equal to 0. So, for a linear transformation A to be invertible, I will say linear transformation A 2 by 2. Again, I will just make this very clear, we are only working with 2 by 2 matrices right now. To be invertible, determinant of A must not be equal to 0. If this happens, then all the linear transformations that we have studied before, if all of them have determinant to be not equal to 0, I will leave that as an exercise to the viewers. You could probably try out the determinant of all those matrices that we have studied for linear transformations, find out the determinant. If it is not equal to 0, definitely the transformation is invertible. That means the map is invertible. You go from the vector u to v under the effect of A, you can actually come back from v to u under the effect of A inverse. You can actually do that, right. Now, the question is, when will the determinant be equal to 0? When will determinant of A 2 by 2 matrix be equal to 0? Then we will be able to make much more inferences and much more conclusions. So, the question is, when will be? So, let us write this. When will determinant of A 2 by 2 be equal to 0? So, let us look at that. When will determinant of A 2 by 2 be equal to 0? Let us see what happens. So, how did we define the determinant? Determinant of A 2 by 2 is A11 A21 A22 minus A12 A22, and if determinant of A 2 by 2 is 0, this simply means A11 minus A11 A22 minus A12, I am sorry, I have written this should be A21, sorry, that is A21, A12 A21 is equal to 0. This implies A11 A22 is equal to A12 A21. I can write this as A11 by A21 is equal to A12 divided by A22. Essentially what we are trying to say is, if you have a matrix whose columns are A11 A21 and A12 A22, we say that the determinant is 0 if the columns of A 2 by 2 are multiples of each other. Now, what do we mean by that? For example, we will take this matrix A, which is 2 1 4 2. Now, we clearly see that determinant of A in this case is 4 minus 4, which is 0. Now, if you look at if you pay attention to the two columns of this matrix A, you see that 2 1 and 4 2, let us assume that okay, this is 1 2 3 4 1 2 3 4. So, the 2 1 matrix is basically the 2 1 vector is basically in this direction. Now, 4 2 vector is also along the same direction that you see, which means in this case there is no parallelogram formed right, there is no parallelogram, therefore, the area is 0 in this case. That means how do we get back to how do we put all these things together? You remember we did this idea of linear independence and linear dependence sometime back in one of the previous classes, where we said that if the two vectors are parallel, that means they are going to be linearly dependent. So, in this case we see that one of the columns can be written as a multiple of the other, which means they are in the same direction, therefore, they are linearly dependent. Therefore, when we have, if we have a matrix, a 2 by 2 matrix whose columns are multiples of each other, then you will not have a parallelogram to be formed, and therefore, the area is 0, which means the determinant is 0, and therefore, the matrix, corresponding matrix is not invertible. Now, in fact, it makes even a bigger sense now if we are able to connect all these things to the set of linear equations, solving the system of linear equations that we studied in the first two modules. We will look at that in a minute, right. So, recall. So, we will connect all these things. So, what did we say? A transformation is invertible. I think we made that comment there. We said that a transformation is invertible only if the determinant of A is not equal to 0, right. Now, what we do is we basically look at system of linear equations, which we have already done in module 1, and we are going to look at it in a completely different perspective right now, system of linear equations in so we are going to restrict ourselves right now with 2 equations, 2 unknowns, right, because that is easy, because we are doing only that right now. So, we will say 2 equations and 2 unknowns. So, when we did this 2 equations and 2 unknowns, okay, probably let us write the equations again. A11 x1 plus A12 x2 is equal to B1, and A21 x1 plus A22 x2 is equal to B2. This is what we had. Now, we know that the matrix, you have this matrix A11 A21 A12 A22 into x1 x2, that means it transforms this vector x1 x2 to this vector b1 and the vector b1 b2, right, the vector b, which is basically denoted by the 2 components b1 b2, right. Now, we are going to do something interesting here. What is that? We are going to say that the vector b, which is basically b1 b2 represented by these 2 components, now can be written as a linear combination of the columns of the matrix A, where I am going to write this as x11 into A11 A21 plus x2 into A12 A22. We see that the right hand side vector b that we had is it's basically a linear combination of the column vectors of the matrix A. That means we are right now looking at the column perspective of this given matrix, right. So, the question is, even here we had serious issues. We wanted to know if, so we wanted to know that so the questions that we had is like, when does A 2 by 2 x, that is a 2 by 1, you are going to get B 2 by 1, when does this system of equation have unique solution, no solution, unique solution, 1, 2, infinitely many solutions, 3, no solutions. Right. We encountered this when we did system of equations and we were trying to figure out we actually looked at the kind of geometry, in the sense we looked at the whether the lines were intersecting or the lines were overlapping or the lines were parallel to each other, that there could not be any solution at all. Now, in our context right now, how are we going to connect the idea of the system of linear equations to the idea of linear transformations, because after all this matrix we just saw that it transforms this vector x1 x2 to this vector b1 b2. So, the question now is, can we relate all that we have studied in terms of transformations to the system of equations and say, okay, is there a way in which I can look at a system of equations from the perspective of vectors, linear combinations of vectors, and then conclude whether if I can have unique solution, infinitely many solutions, or no solutions as far as a 2 by 2 system of equation is concerned. And that is something which we will look at in the next lecture. As of now, we have covered in this module, we have covered a lot of ground on the linear transformations, different linear transformations that we have covered. Then we actually did I mean, we looked at invertible linear transformations and non-invertible linear transformations. We basically figured out what is the condition for a transformation to be invertible. I mean, again with the disclaimer that we are working on only 2 dimension. So, we figured out that there is something called as determinant for the matrix A, and we told that the determinant corresponds to the area of the parallelogram enclosed by the columns of a matrix A. That means you take a matrix A which is 2 by 2. So, you will have a parallelogram, you may have a parallelogram to be formed by the 2 columns of the matrix A, and if there is a parallelogram, it will enclose an area, and if that area is I mean if it is a non-zero area, then you have the transformation to be invertible, the matrix is invertible. And we also looked at what happens if when the determinant is 0. That means we said that both the vectors are actually linearly dependent. So, in the next lecture what we will do is we will try to address this particular idea of when does a system of 2 by 2 linear equations will have unique infinitely many solutions or no solution from the idea of vectors, and after that we look at the idea of eigenvalues and eigenvectors for linear transformation. Thank you.